Page 1 of Transformations Addendum. Let's see. The function y equals f of x is transformed to the function y equals 3 plus 2 times the function 1/2 x plus 1. Fully describe the transformation that maps y equals f of x onto this function. Okay. Let me show you the order that you should look at this. First, you should look inside the f of x function. I think it's easier to do the width adjustments on the function before you start translating it up. So I would first you're going to do the outside one. So like everything inside the function parentheses works in the opposite order of PEMDAS. So here you would say the plus 1 comes at the end, so you do this one first. And then you do the multiplication by a half, that would be second. And then outside the function, you do everything in the order of PEMDAS. So you would do the inside thing first, multiplying by 2, and then finally you would do the addition of 3. Okay? So now if on the inside you had an expression like this, x minus 2 divided by 2, or x plus 2 instead of divided by 2, now in PEMDAS here, the last thing to be done would be the divided by 2, so you would do that first, and then you would do this, okay? But since we're doing this one here, we will do the addition of 1 first, okay? All right. So the transformation that is going to be done, let's see, step 1 is the plus 1. And the plus 1 is going to be a translation to the right or left. Well, the plus 1 inside the function is interpreted kind of backwards. So since it's plus 1, sounds like it's going to the right, it's actually going to go to the left. Okay? So translation to the left by 1 unit. That's the first step. Second step is you are going to do a horizontal stretch by a factor of 2. Okay, so do you see how the 2 is on the bottom? That is the stretch factor, the denominator. Okay. Third thing you're going to do is you're going to do a vertical stretch by a factor of 2. And the fourth thing is you're going to translate up by 3. Okay. All right. So we did A. Now B, it says, given the following points lie on f of x, find the coordinates of the point each moves to under the transformation, and they give us the same transformation. So first we're going to do it for 1, negative 3. Okay? So the first thing that's going to happen to 1, negative 3 is we're going to translate left by 1. So the x coordinate is, instead of 1, is going to be 0, right? So we'll go 0 and then negative 3. The y coordinate does not change under translation to the left. Next step is we're going to do horizontal stretch by 2. When we do the horizontal stretch by 2, that means that the horizontal coordinate, which is 0, is going to move from the axis, from the y-axis, by a factor of 2. Now, it's already on the y-axis, right? 0, negative 3 is here, right? It's already on the y-axis, so it's not moving anywhere. Even though we're stretching by a factor of 2, nothing happens. So, stays put. Number 3, vertical stretch by 2. Now the vertical coordinate is going to change. So negative 3 is going to get 3 times farther from the x-axis because it's a vertical stretch, and it will go from negative 3 to negative 6, right? Last of all, we are going to do a translation up by 3. So 0, negative 6 is going to become 0, negative 3. Okay? Let's do the same thing to negative 1, negative 3. Okay. So first step, we're going to do translation left by 1. It's at negative 1, negative 2, which is here. So it's going to move 1 to the left, so it's going to be negative 2, 2. Next step, it's going to do a horizontal stretch by 2. Now it's here, right? A horizontal stretch is going to move, right now it's 2 units away from the center. It's going to move 4 units away from the center because it's going to be the horizontal stretch by a factor of 2. So now it's going to be -4, -2. Now it's going to do a vertical stretch by 2. It's at 2 units away from the y-axis. Now it's going to go to 4 units away from the y-axis. So now it's going to be -4, -4. Last of all, it's going to translate up by 3. Now it's here, okay? So it's going to go up by 3. So I'm going to use a different colored pencil here. 1, 2, 3. So now it's going to be here, which is -4, -1. Okay? Let's move on to the next one. Okay, now in part C, it's actually asking the reverse. It's saying, okay, these 2 points are the destination after you undergo all these changes. Can you find the original point, which ended up being the point -2, -5? So basically, we're going to do the transformations backwards and in the reverse order. Okay, so let's see. For -2, -5. We'll start with -2, -5 is like the last step, right? And how did we get there? We did a translation up by 3. So to get to step 3, which is the previous step, we are going to do a translation down by 3. So that would be y equals -5 would go even lower. It would go to -8, right? How do we get to step 2? Well, step 2 was horizontal stretch, or step 2 to step 3, the transformation was vertical stretch by 2. So we would do a vertical stretch by 1/2 instead to go backwards, right? So instead of -8, we would be at -4. Okay. Now, how do we get back to step 1? So step 1 was a horizontal stretch by 2. So we're going to go backwards. We're going to do horizontal stretch by 1/2. So instead of -2, we would have -1, -4. And then last of all, how do we get back to the original? The original, we need to do the opposite of translate left by 1. We're going to translate right by 1. So instead of -1, it's going to be 0, -4. That would be the original point for this one. Now we'll do the backwards of this one, 5, 0. So we're going to start out with 5, 0, which was found by doing step 4, which is a translate up by 3. We're going to reverse that. We're going to do a translate down by 3. So we're going to have 5, -3. Now, how did we get to step 3? We did a vertical stretch by 2, so we're going to do the opposite of that, a vertical stretch by 1/2. So we'll do 5, -1.5. Then we're going to undo step 2, which is horizontal stretch by 2. We're going to do horizontal stretch by 1/2. So the 5 is going to become a 2.5. Now we're going to undo the last step, which is translate left by 1. We're going to translate right by 1. So the 2.5 is going to become a 3.5. So 3.5, -1.5. So that was the original point then. Okay. 5D, reflections. The function y equals f of x is transformed to m of x equals the inverse function of f. Find the image points on m of x for the following points on f of x. Okay, one thing you need to remember about inverse functions is that inverse functions can be found by reflecting about the diagonal line y equals x. Okay, so let's say I have a point 3, 1. What does that look like when you reflect it about y equals x? It becomes the opposite, which is 1, 3. So you just take the y coordinate, you make it the x, you make the x coordinate y, and that gives you a point which is reflected about the y equals x axis. And it makes sense, right? When you take the inverse function, basically what you're doing, the first thing you do is variable interchange. Remember when you do the algebra process to find the inverse function? So you are taking the x values and making them y, and taking the y values and making it x. So it makes sense that the inverse function and the function are related by a reflection about the y equals x axis, and you're reversing the x and y coordinates to find them. So this is pretty easy here, actually. So the image points on m of x, which is the inverse function for the following points, is basically you're going to reverse the 3 and the 1 to 1 and the 3, because the x becomes y and the y becomes x. So this is like super easy. You just like reverse these. Okay? Find the points on f of x corresponding to the following points on m of x. Okay, so m of x is the inverse, f of x is the original function, but actually you're going to do the exact same thing. If you're finding points on the inverse function given the function points, you're going to reverse them. If you're finding the points on a function given the inverse function, you also reverse them. So this is super easy. Okay? I think the difficult part is just thinking about it. To do it, it's a no-brainer. 5f, simple rational functions. A function of the form y equals ax plus b over cx plus d, where x is not equal to negative d over c, where a, b, c, d are constants, is called a simple rational function. This is the same functions that we worked with in 10th grade, like 1 over x plus 1, or 1 over x, or x plus 5 over x plus 1. Okay? Why can't the x value be negative d over c? Well, try it out. Try to put negative d over c in for x in the denominator. What happens? You're going to end up with negative d plus d, or 0, and the denominator is 0, and we know that creates an asymptote. So basically that's a value that's not in the domain. It is also the value of the asymptote. These rational functions have both vertical and horizontal asymptotes. Because remember, these rational functions look kind of like this. So you can see that here and here we have a vertical and horizontal asymptote. They can be graphed by transformations of the parent functions y equals 1 over x. Y equals kx is a vertical stretch of scale factor k, right? Because basically what I did was I multiplied 1 over x times an a value, a scaling constant. 1 over x minus k is a horizontal translation to the right through k units. Okay, that makes sense, right? Because remember, if you have f of x minus k, that means that this is a horizontal translation to the right by k. Okay, all right. Moving on. Number 1, write in the form ax plus b over cx plus d the function that results when y equals 1 over x is transformed by, and they give us a whole bunch of different transformations here. Let's get rid of this first. Okay. So, a vertical stretch with a scale factor of 1/2. Okay. So you start out with 1 over x. And then we're going to do a vertical stretch with scale factor 1/2. Remember that the way you do that is you simply multiply 1/2 times the whole function, or times the parent function. So basically, the answer is you could either write 1/2 over x, or you could have 1 over 2x. Okay. I'm going to write it as like 1/2 over x, and I'm going to show you why later. Okay. Let's do B. A horizontal stretch with a scale factor of 3. Okay, now remember, to do a horizontal stretch with a scale factor of 3, you basically put divided by 3 inside with the x here. So in this case, you would put 1 over, and instead of x, you would put x divided by 3. So actually, it looks kind of weird, doesn't it? I mean, if you simplified it, you would want to do x divided by 3 is the same thing as multiplying by 3 over x, so it would end up being 3 over x. Okay? Now, the reason why I prefer at this point to write it like this is because it looks like a horizontal stretch. When you look at this, what does it look like? It looks like a vertical stretch, right? When you look at this, what does it look like? It looks like a horizontal compression, okay? Because it's together with the x in the denominator. So the thing is, with a lot of functions, many different types of functions, horizontal stretches look like vertical compressions, and horizontal compressions look like vertical stretches, because it's kind of like that thing where it's like, I'm not really fat, I'm just too short, right? It's like, how can you tell the difference between someone who is too fat from a person who is too short? When you have a function that goes off into infinity in all directions, you can't tell if the person is tall or not, right? Because it goes off to infinity, right? So basically, just to show that this is actually a vertical compression, I leave the 1/2 in the numerator. Just to show that this is a horizontal stretch, I leave the divided by 3 right under the x. Okay, just to make it a little bit more intuitive about what it is. But actually, rational functions are not good functions to show the difference between horizontal compression and vertical stretch, because they look the same. Okay, in the end, it's the same thing. What are good functions to show the difference? Well, functions that don't go off into infinity in all directions, such as you could use maybe log. You could use trig functions. Those trig functions are really good to show the difference between horizontal compression and vertical stretch, because it's not the same thing for a trig function. Okay, let's do C now. A horizontal translation of -3. So horizontal translation of -3, remember, we kind of do this, right? So the way we do that is we do f of x minus a -3 minus a -3, because the default is to do a minus. And if it's minus -3, then it's going to end up being f of x plus 3. Okay? So we're going to have 1 over x plus 3. That is a horizontal translation of -3. Now we're going to do D, a vertical translation of 4. So remember, a vertical translation, basically what you do is you take the original function and you just add the translation factor. So we'll have 1 over x plus 4. Okay? So that's it.